Aircraft engines drive aviation forward, crafted through precision manufacturing, evolving in diverse types, and seamlessly replaced to ensure safety and performance. Or, the production of the Angara A5 rocket, one of Russia's most advanced space launch vehicles, represents a massive industrial and technological achievement. The process begins with design modernization. Old paper blueprints, numbering over 400,000 sheets, are carefully digitized into 3D models. This digital transition enables engineers to save significant time and costs during assembly while ensuring precision in every component. A central element of the rocket is its powerful liquid fuel engine, the RD-191, developed at NPO Energomash near Moscow. The engine's combustion chamber reaches temperatures of 500 degrees Celsius and pressures exceeding 250 atmospheres, conditions so extreme that they rival those in the Mariana Trench. Each engine requires about 3 months of assembly, after which it undergoes fire tests. Exhaust gases exit the nozzle at 3.5 kilometers per second, with their immense energy dissipated into a closed water basin before being released as harmless steam. Workers treat these engines almost as works of art, with responsibility and pride deeply rooted since the Soviet era. Meanwhile, in Omsk, at the Poland Production Association, the rocket's modular structure is fabricated. Sheets of aluminum alloy are bent and joined using friction stir welding, a technique that heats metal through friction before bonding. This produces seams as strong as the base material and nearly eliminates defects. The welded cylindrical shells then move to the tank workshop, where bottoms and flanges are attached. These tanks form the massive fuel compartments of the rocket, resembling giant metal cylinders prepared for integration. Next comes the installation of electronic systems. In the final assembly hall, universal modules arrive coated in black insulation. Here, engineers fit precision instruments, thousands of sensors, and kilometers of wiring. Every component is Russian-made, as the philosophy of Angara emphasizes technological independence. Cooperation across dozens of enterprises, from Bryansk to Siberia, ensures the supply of high-quality parts. Cleanroom procedures are strictly followed. For example, technicians sterilize fuel tank surfaces to prevent dangerous chemical reactions, treating their work with surgical precision. The assembly culminates with the integration of the RD-191 engines, aligned with micrometer accuracy. At this stage, the rocket takes its full shape, resembling a towering metal giant. Finally, the completed vehicle is transported to the Plesetsk Cosmodrome for launch preparations. The Angara A5 embodies a new era for Russian spaceflight: reliability, ecological safety, and cost efficiency. Its modular design allows multiple configurations for different missions, from near-Earth orbits to future lunar programs. Beyond its engineering brilliance, Angara is also a symbol of industrial renewal, uniting thousands of workers across Russia into a single vision of advancing space exploration. A gas turbine is a highly advanced machine that converts chemical energy from fuel into mechanical energy, and ultimately into electrical energy. Its operating principle is based on the Brayton cycle, which involves 3 major sections: the compressor, the combustor, and the turbine. First, ambient air is drawn into the compressor section, where multiple stages of rotating blades compress it to a high pressure. This compressed air is then delivered to the DLN 2.6 plus combustor with axial fuel staging, where fuel is injected and burned at extremely high temperatures. The advanced combustion system enables higher firing temperatures, increasing efficiency while reducing emissions. The hot, high-energy gas expands through the turbine section, where it drives the rotor blades. This converts thermal energy into mechanical energy, rotating the drive shaft, which is connected to a generator that produces electrical energy. Modern HL-class turbines represent the next generation of this technology. They are designed for unprecedented levels of performance and efficiency. Innovations include a robust advanced combustion system, optimized sealings and coatings that withstand higher firing temperatures. These coatings, along with super-efficient internal cooling features, reduce the consumption of cooling air, enabling more power output and operational flexibility. Together, these improvements provide higher reliability, fuel efficiency, and lower operational costs. The manufacturing and assembly process of a gas turbine involves both precision engineering and advanced inspection technologies. At the core is the rotor, which must be perfectly balanced to ensure safe and efficient operation. Rotor balancing is performed in a specialized balance bunker, where high-speed adjustments guarantee minimal vibration. Components undergo white light scanning to capture precise surface geometry, while ultrasonic testing and fluorescent penetrant inspection ensure there are no internal flaws or cracks. Many rotor parts are produced or restored using CNC machining and welding. Worn diaphragms and rotors can undergo weld restoration before being remachined to exact tolerances. Spare bearings and oil seals are fitted to ensure smooth rotation, and technologies such as OPS-PEE are applied for fine-tuning high-speed performance. Once the rotor passes inspection, the blade assembly process begins, where turbine blades are mounted with precision to withstand extreme temperatures and rotational speeds. The production of new rotors follows strict engineering standards, combining welding, machining, and inspection processes until the finished rotor is approved. Finally, the complete gas turbine is assembled, combining the compressor, combustor, turbine, and generator into a single power-producing unit. In conclusion, gas turbines are masterpieces of modern engineering. Their ability to convert fuel into vast amounts of reliable electricity with high efficiency makes them essential in today's energy landscape. With innovations such as HL-class designs, advanced coatings, and precision manufacturing methods, gas turbines continue to push the boundaries of performance, flexibility, and sustainability. At Goodwin Hall, Virginia Tech proudly showcases a Rolls-Royce jet engine, symbolizing innovation and engineering excellence. This powerful engine represents advanced aerospace technology, inspiring students, researchers, and visitors to explore the future of aviation while honoring the strong partnership between Rolls-Royce and Virginia Tech. Jet engines, also known in Italian as esoriatori, are propulsion systems that rely on ambient air as the oxidizer for combustion. Their assembly requires extreme precision, as every component must operate under high temperature, pressure, and rotational speed conditions. The process begins with the construction of the compressor section. Rows of rotating and stationary blades are carefully fitted onto the shaft, forming stages that will progressively compress the incoming air. Each blade is inspected for balance and alignment to guarantee efficiency and safety. Following this, the combustion chamber is assembled. Here, compressed air will mix with fuel and ignite, producing high-energy gases. Technicians install fuel nozzles, liners, and igniters with close attention to detail, since even small imperfections can lead to unstable combustion. Once the chamber is secured, the turbine section is added. The turbine blades, often made from advanced alloys, must withstand extreme heat while extracting energy from the expanding gases. These blades are mounted onto discs with microscopic tolerances, and cooling passages are integrated to protect them from thermal stress. Afterward, the exhaust system is installed, shaping the flow of gases and generating thrust. The casing and external structures are then mounted to enclose and protect the core. Throughout the process, rigorous inspections and torque measurements are performed to ensure reliability. Finally, the completed engine undergoes functional testing, where it is operated under controlled conditions to verify performance, stability, and safety before being installed on an aircraft. Thus, assembling a jet engine is a delicate combination of engineering expertise, precision craftsmanship, and advanced materials technology. By efficiently transforming chemical energy into thrust, the reator remains the essential heart of modern aviation propulsion. Engineers operate the engine control system to maneuver it precisely into the XWB horizontal build variable height access platform. The platform is designed to adapt to the contours of the engine, ensuring that it is securely positioned during the build process. By adjusting its height, the platform provides engineers with safe and convenient access to all required areas, eliminating the need for unstable or improvised working arrangements. This controlled movement not only increases safety, but also enhances efficiency, allowing multiple tasks to be carried out simultaneously at different levels. The platform's variable height function ensures flexibility for complex assembly operations, while its robust structure maintains stability throughout. As a result, engineers can perform detailed work with improved ergonomics and reduced downtime, making the entire assembly process smoother, safer, and more productive. The production of the GTU-32 Ledoga follows a structured process divided into several stages to ensure precision and reliability. At Nevsky Plant, manufacturing begins with the metallurgical complex, where casting provides all necessary components, ensuring full self-sufficiency in foundry parts. These castings are then transferred to machining facilities for precise shaping, after which welded assemblies are fabricated in the boiler welding complex. Initially, auxiliary frames and support systems for the turbine are localized and manufactured. The next stage involves partial assembly of the turbine with in-house production of casing components. In the advanced stage, up to 90% of components are locally produced, assembled, and prepared for delivery. Assembly starts with positioning the rotor inside the gas generator housing, which features a horizontal joint. Once enclosed, the generator is connected to the low-pressure turbine. The entire unit is then mounted onto a special frame before being transferred to the testing facility. The sun At the testing stand, auxiliary systems such as the starting unit, oil service system, and fuel supply are installed on a separate frame, forming a complete 18-meter-long setup. Fuel gas from the city network is compressed from 8 to 31 atmospheres and supplied for full-scale testing. Here, efficiency, power output, and shaft speeds are verified. Finally, after successful trials, the GTU-32 is transported for packaging and shipment, delivered as a turnkey, factory-ready gas turbine unit. Technicians begin by disconnecting all fuel, hydraulic, and electrical lines from the Pratt & Whitney JT9D-7R4G2 engine. Next, the mounting hardware securing the engine inside the large test cell is carefully unfastened. With lifting equipment, the engine is gently lowered onto a transport stand. Finally, it is moved out of the test chamber, ensuring safe handling and preparation for inspection or maintenance. Skilled engineers undertake the replacement of the 5-ton Rolls-Royce Trent 500 engine on the Airbus A340-600. The aircraft is carefully positioned inside the hangar, where the massive engine is suspended from the ceiling to allow precise handling. Despite its enormous size, the entire replacement process can be completed within 24 hours. The engine, which powers the A340-600, contains turbine blades capable of producing 900 horsepower, while each fan blade can generate an astonishing 1,000 tons of force, comparable to the weight of a freight train. Once the new engine is securely installed and checked, the aircraft is wheeled out, ready for service. The dismantling of the Angara A1.2 launch vehicle is carried out with precision and strict adherence to safety regulations. After transportation from the assembly site to the Plesetsk Cosmodrome Launch Complex, the rocket is carefully positioned in its service area. Specialized ground crews begin the process by disconnecting external power, fuel lines, and communication systems. Step by step, the boosters, payload fairing, and core modules are separated using cranes and handling equipment designed specifically for rocket operations. Each stage is systematically lowered, secured, and transferred to designated storage or maintenance facilities. This procedure ensures that no component is damaged, and that all sections can be inspected for reuse, testing, or preparation for future missions. The dismantling process highlights the advanced engineering behind the Angara program, which relies solely on Russian industrial and scientific capabilities. The Angara A1.2 is part of a broader national strategy to secure independent access to space, allowing Russia to launch satellites and other spacecraft of various classes directly from its own territory. By carefully managing both assembly and dismantling operations, engineers maintain reliability, extend the lifespan of equipment, and support the long-term development of Russia's space exploration infrastructure. Perm Plant is one of Russia's giants in aviation and industrial engine manufacturing. With a proud history of creating engines for transport and civil aircraft, today it develops innovations shaping the nation's future. Its gas turbines power energy and pipelines, while young specialists drive progress toward producing up to 270 advanced engines annually by 2027. The manufacturing and assembly of a modern jet engine is one of the most complex engineering achievements in the aerospace industry. The entire process of producing and assembling components takes about 2 years, while the design and testing phase can last up to 5 years for each model. Every part must meet strict standards of safety, durability, and efficiency before the engine is approved for use in aircraft. One of the most crucial components is the fan blade, located at the front of the engine. Fan blades play a vital role in creating thrust which propels the aircraft forward. Each blade consists of 2 blade skins produced by forming molten titanium in a hot press. Once removed, the blades weigh about 40 pounds each. To enhance durability, each blade skin is welded to a hollow material core. This cavity is then filled with a combination of titanium and honeycomb structure, ensuring both strength and lightness. The special aerodynamic shape of fan blades allows them to efficiently push air in the opposite direction, generating the reaction force necessary for flight. Another key component is the disc, a solid core to which the compressor blades are attached. This disc resembles a large wheel and must be extremely strong and free of imperfections. Even the smallest crack could develop into a major defect under the immense pressure and heat of engine operation. Traditionally, discs were manufactured by cutting a solid metal billet, heating it, and stamping it into the required shape. This process also helped seal microcracks. However, modern jet engine manufacturers increasingly use powder metallurgy, a sophisticated method that ensures higher purity and durability, making discs even more reliable. The engine assembly process begins with the engine mounted vertically on a fixture to allow easy manipulation. Assembly typically proceeds from the rear forward. First, the high-pressure turbine, located closest to the combustion chamber, is bolted to the low-pressure turbine, positioned further away. Afterward, the combustion chamber is securely attached to the turbine assembly. Advanced computer numerically controlled robots are often used at this stage. These robots can weigh each turbine blade, analyze it, and place it precisely on the shaft to create a balanced turbine, which is essential for smooth operation. Once the turbine and combustion chamber are in place, the compressors are installed. Both the high-pressure and low-pressure compressors are carefully aligned and connected. The fan, together with its frame, is then assembled at the very front of the engine. Following this, the main drive shaft is installed, linking the low-pressure turbine to the fan and compressor system. This connection allows the turbines, driven by exhaust gases, to power the front fan and compressors, completing the engine core. Finally, the exhaust system is installed at the rear of the engine, after which the engine is fully assembled and ready for shipment. Once delivered to the aircraft manufacturer, the engine is integrated with the aircraft's plumbing, wiring, and aerodynamic skin. In conclusion, the production of a jet engine requires high precision, advanced technology, and meticulous craftsmanship. The piston engine overhaul process at Western Skyways begins with disassembly. Engines are unloaded, photographed in detail, and carefully separated so that each component remains assigned to its original engine. Parts are stored on individual carts to prevent mixing. Next, all components go through cleaning and inspection. Oil, grease, and carbon deposits are removed using soda blasting, washing systems, and other machines. Aluminum housings and cases are examined with fluorescent penetrant under black light to detect cracks. Steel parts such as crankshafts, connecting rods, and gears are checked with magnaflux testing. Damaged components, like cracked crankshafts from prop strikes, are rejected. Pero during inspection, Western Skyways applies both static and dynamic balancing. Unlike factory standards that allow variations, each piston, pin, and connecting rod is weight-matched for precision. Crankshafts are spin-tested and dynamically balanced before final assembly. The machining department ensures close tolerances on rods, rockers, and starter adapters, working within thousandths of an inch. This guarantees that rebuilt parts meet aerospace-level precision. Meanwhile, accessories are overhauled. Teams service starters, alternators, magnetos, fuel injection systems, and turbochargers. Each accessory is disassembled, repaired, and bench-tested to ensure reliability. Specialized crews handle different systems, including fuel injection flow benches custom designed by Western Skyways to test both Continental and Lycoming units simultaneously. Finally, prepared crankshafts, balance connecting rods, and machine components are reassembled into cases that have been sealed with bearings, high-R, and silk thread to prevent leaks. Each engine undergoes strict, non-destructive testing and compliance with service bulletins before moving forward to the build-up line. Through this structured process, Western Skyways ensures each overhauled piston engine meets or exceeds factory specifications. The Boeing 747-400 of KLM begins its departure from Curaçao with a powerful engine start sequence. Each of the 4 engines is carefully activated, producing the deep rumble characteristic of this iconic aircraft. Ground crews complete final safety checks while the plane slowly taxis to the runway. Once aligned, the pilot advances the throttles, and the engines generate immense thrust. The aircraft accelerates rapidly, its wheels steadily lifting from the runway. With graceful power, the 747-400 climbs into the sky above the Caribbean, marking another safe and majestic takeoff from Curaçao. The Boeing 747-400F begins its departure sequence with a powerful pushback from the gate, guided by ground crews to ensure safe maneuvering. Once aligned, the aircraft's 4 engines are started one after another, each producing a deep roar as they spool up to idle power. Ground personnel monitor the process closely while the flight deck confirms stable parameters. With engines running smoothly, the pushback tug disconnects, and the aircraft transitions to taxi. Slowly, the massive freighter rolls toward the runway, its wings flexing slightly under the weight of fuel and cargo. At the threshold, the pilots advance the throttles, unleashing tremendous thrust. The aircraft accelerates steadily, gaining speed until rotation is initiated, lifting gracefully into the sky and beginning its long-haul journey.